At first glance, it looks perfectly ordinary. A bright coma, a soft diffuse halo, the familiar glow of a comet moving through the inner solar system, exactly what physics predicts, exactly what we've seen thousands of times before. But that brightness is a trap. Hidden inside the light, buried beneath the symmetry, is a structure so precise, so mathematically rigid, that it is quietly forcing astronomers to reconsider what this object actually is. New high-resolution orbital data has just been released. And what it reveals changes the entire conversation. To find the truth, astronomers applied a technique called rotational gradient processing, a filter that mathematically cancels anything perfectly circular and symmetric. Rotate the image, subtract it from itself, and everything natural and round simply vanishes. What remains is only what symmetry cannot explain. When this filter was applied to C/2024 G3 Atlas, the coma disappeared entirely. And what emerged from the silence was not chaos, not random outgassing, not the turbulent mess of a thermally stressed icy body. It was geometry. 3 perfectly defined jets arranged in a symmetric triad, each separated from the next by exactly 120 degrees. Not approximately. Exactly. That precision alone would raise eyebrows. But it's what happens next that makes this impossible to dismiss. The same processing was applied across multiple high-quality observation sets spanning nearly 2 months, late November, December, and into January. And in every single dataset, the same triadic structure appears. Same angular separation. Same symmetry. Same stability. In a natural comet, jets are chaotic. They shift as the nucleus rotates, flicker as new fractures open and old vents close. But here, the geometry does not change. It remains anchored, as though it is part of the object's internal architecture rather than a surface accident. A fourth structure compounds the mystery further, a dominant elongated jet extending in the solar direction, far more powerful than the other 3, forming a clear axial feature. The complete picture becomes highly specific, 3 short symmetric jets at 120 degrees, plus 1 dominant solar-directed plume. A configuration that standard comet models were never designed to explain. And the deeper you look, the stranger it gets. Jets are not merely visual features, they are forces. Every kilogram of material expelled produces a reactive impulse in the opposite direction. 3 symmetric jets plus 1 dominant jet create a complex torque system that, in any loosely bound rubble pile, should destabilize rotation, scramble orientation, and produce chaotic spin behavior. Instead, analysis of the jet motion reveals something that stops researchers cold: rhythmic oscillation. A controlled, periodic wobble consistent with precession, not instability. From this motion, astronomers have reconstructed a rotational period of approximately 7.1 hours, giving the object what amounts to an internal clock. The jets trace conical paths through space rather than random spirals, suggesting a dynamical balance that feels less like a tumbling fragment and more like a rigid body responding predictably to applied forces. 1 anomaly can be noise. 2 can be coincidence. But they keep stacking. There is also the matter of perspective. Every image we receive is a 2-dimensional projection of a 3-dimensional system. This matters because random jet distributions in 3-dimensional space almost never project into perfect symmetry repeatedly over time. As Earth, the Sun, and Atlas move continuously relative to one another, the viewing angle shifts. If these jets were random fractures, their apparent separation should distort and fluctuate. Instead, the 120-degree geometry holds across changing observation epochs, implying that the symmetry is not an artifact of where we happen to be standing, it is something that exists regardless of where we observe it from. Projection artifacts vanish under changing geometry. Intrinsic structure does not. Then comes the mechanical contradiction that no model has cleanly resolved. For an object of this size, a 7-hour rotation generates significant centrifugal forces. Combined with sustained mass loss from active outgassing, a loosely bound aggregate should be pushing toward fragmentation, visible deformation at minimum. Yet the nucleus remains coherent. The jet geometry remains stable. The oscillating motion repeats rather than degrades. This implies either internal cohesion far beyond what is normally assumed for cometary bodies, or a mass distribution precisely configured to counteract destabilizing forces. Either possibility sits uncomfortably outside the standard classification. A body that can rotate rapidly, sustain asymmetric outgassing, and preserve macroscopic symmetry across weeks of thermal stress is not behaving like dirty ice loosely stitched together by gravity. And this structure does not exist in isolation. The symmetric triad appears alongside a persistent non-gravitational acceleration that resists standard outgassing explanations, an unusual antitail structure, polarization signatures that diverge from comet norms, and chemical behavior that shifted measurably before and after perihelion. Each feature, taken alone, might be rationalized away. Together, they form a cumulative burden that simple models struggle to carry. The question quietly changes from whether nature can produce one strange feature to how often it should produce all of them simultaneously. When the answer trends toward almost never, the responsible response is not to reach for extraordinary conclusions, but to acknowledge that the current classification may simply be incomplete. Nature is capable of symmetry. But context matters enormously. Symmetry thrives at microscopic scales, in crystals, molecular bonds, fractal growth patterns, where energy minimization governs everything. At macroscopic scales, in a thermally stressed body actively losing mass, symmetry is fragile. It breaks easily and rarely survives prolonged perturbation. What we observe here is not passive, decorative symmetry. It is functional symmetry interacting dynamically with rotation, torque, and momentum. The jets are not static features etched into ice, they are active processes that should amplify instability, not suppress it. When an object repeatedly chooses order where chaos would be far cheaper, the universe is signaling that something about our assumptions may need revision. On January 22, 2026, a rare geometric alignment brought the Earth, Atlas, and the Sun into near-collinear configuration, reducing projection distortions to their minimum for this entire encounter. Back illumination enhanced the signal, faint structures grew brighter, and edges sharpened. For the first time, this object's architecture became visible with minimal distortion. Whatever the geometry truly is, this was the window in which it would either hold or break down under scrutiny. The results are still being analyzed. But one thing is already clear. Science advances not when mysteries are solved, but when uncertainty collapses into a smaller, sharper set of possibilities. Atlas has done exactly that. Symmetry that should have collapsed has not. Rotation that should have destabilized has not. Jets that should have wandered remain anchored. Across weeks of thermal stress, shifting illumination, and changing geometry, the structure endures, repeating, persisting, and revealing an internal order that standard models absorb only by stretching themselves uncomfortably thin. This does not mean we have an answer. It means we have reached the point where pretending the question is simple is no longer scientifically honest. The geometry has spoken. Now we have to decide whether we are ready to listen.